So we've looked at how to find important lines and points, chords and tangents and what have you. Let's now look at some different theorems using those. So focal chords, you remember we talked about focal chords, which is simply a chord that passes through a focus. Turns out that if you draw a tangent at the end of the focal chord, then that point of intersection will meet on the directrix, but they'll also meet at right angles. So if we had to prove that particular property, well, remember back in focal chord, I said usually what they want us to do is prove PQ equals -1. And there were a couple of ways we could do it. Whether or not we'd already found the equation of the chord. If we had, we'd just substitute the focus into that equation. Out comes this relationship. Otherwise, we'd just equate the two slopes. Slope PQ equals slope PS. And we come up with this relationship PQ equals -1. But remember, the slope of the tangent we found out was indeed the parameter. So the slope of the tangent of P is P, the slope of the tangent at Q is Q, and we're saying P times Q is equal to -1. So the slopes of the two tangents multiply together to give -1. Well, if that's true, then those tangents must be perpendicular because their slopes multiply together to give -1. So that's how you do the first part, intersect at right angles. The other part is on the directrix. So we could go and find the point of intersection of the tangents. And remember, it ends up being A times the sum of the parameters and then A times the product of the parameters. Well, it's more the Y value I'm interested in. Y is equal to APQ. And again, we've just proved that PQ is equal to -1. So if I substitute that in, Y becomes -A. Well, the equation of the directrix was, so therefore, this point doesn't matter what the X value is. We know the Y value is -A. So it must lie on the directrix. And so to combine the two together, well, that means they meet on the directrix at right angles. Another classic property is what we call the reflection property. It's why headlights in cars are parabolic reflectors. Okay? Well, yeah, don't worry, we don't have to remember this wordy part of it, but technically this is the reflection property. Any line parallel to the axis of parabola is reflected towards the focus. Any line from the focus parallel to the axis of the parabola is reflected parallel to the axis. Thus a line and its reflection are equally inclined to the normal as well as to the tangent. In physics, or junior science for that matter, remember angle of incidence is equal to angle of reflection. That's all it's really saying. Angle of incidence is equal to angle of reflection. So here's a parabola, and what we're saying is any light ray, or this one's coming in, but it'll bounce into the focus. That's also why radar dishes tend to be conics, whether it be a hyperbola or parabola, because hyperbolas have a similar sort of feature. So if those rays come in, it collects at, they usually have the collection point at the focus of the what are they called? Dish, thank you. But a headlight works in reverse. You put the bulb at the focus, and then the light obviously goes out in all sorts of directions. But once it hits the parabola, it'll always bounce parallel to the axis of the parabola, which is why it's useful for cars, because when you're driving along, you don't really need to know what's to the right or left of you. You're more interested in seeing ahead. So it gets all that light and directs it ahead of you. So we want to prove that. So here we are, x squared equals 4ay. What we're going to do is the tangent becomes the straight line that we're going to work out the angle with. Because obviously you can't find an angle with a curve. It's always to the tangent. So I want to show that angle KPS is equal to CPB. I'm going to do it to the tangent. Technically, it's with the normal, because you see, thus a line and its reflection are equally inclined to the normal. So the actual theorem is DPC is equal to DPS. But, as I say, if it's equally inclined to the normal, then it must be equally inclined to the tangent as well, because we know they're perpendicular. So I'm going to prove SPK is the same as CPB. And you'll see there's lots of different ways of proving this particular one. This is just one way of doing it. So angle of incidence equals angle of reflection. Now what do we know? I know that CP is going to be parallel to the y-axis, because we said that when it bounces off our reflector, it's going to go off parallel to the axis of the parabola. So first thing I would do is find the equation of the tangent. So remember that y equals px minus ap squared. That will allow me to find the coordinates of k down here, because that's going to meet the y-axis when x equals 0. So I know that k is the point minus ap squared, or naught minus ap squared. So therefore, the distance from the focus to k is just a vertical distance, so I can just add them together. It'll be ap squared below, and then a above, so the total distance of sk is a plus ap squared. Now I'm going to find distance ps. This one I've got to use the distance formula for because the line's at an angle. So subbing in our points, 0a for the focus, 2ap, ap squared for the point P. And expand out, collect like terms, and you'll see a squareds and everything, so I've taken a out the front. And so we get a p squared plus 1, which was what we just said sk was. So I now know SPK is isosceles because I've got two equal sides. Well, therefore, SPK and SKP, they're going to be the base angles in my isosceles triangle. So SKP and CPB, with our parallel lines, they're going to be equal. Well, if they're both equal to SKP, I know SPK is equal to CPB, and that's what we wanted to prove. I say it's just one way of proving the reflection property. So 9a, just picked out a handful there of properties to play with.